Okay, well, I'd like to welcome Professor Steve Desch to give his Ed Scott lecture. Steve is a professor of astrophysics at the School of Earth and Space Exploration at Arizona State University. He's got a very wide range of interests in formation of stars and planets, chondrules and meteorites. He's PI on a large Nexus NASA grant, looking at particularly life in exoplanets. He did his PhD at the University of Illinois in 1998. And very importantly, he's a fellow of the Meteoritical Society. And probably even more importantly, he's got asteroid 9926 named after him, 9926 Desch. Very nice pedigree. Steve, it's over to you.
Thank you so much. I'm really thrilled to be here. It's just a great chance to be here at the Open University. I'm thrilled to be giving Ed Scott lecture. And I thought I should say I didn't know Ed Scott especially well, but I interacted with him a number of times, and he always was so very nice and soft-spoken and gentlemanly, and a real force in the community to host a number of conferences in Hawaii, and so he's missed. The lecture I'm giving today, I hope, is of somewhat broad interest because it is about short-lived radionuclides in meteorites, but also about what it means for the sun's birth environment. This is a lecture I gave to Protostars and Planet 7 meeting 2 years ago in Kyoto, because I led a book chapter with these co-authors on this very topic. And so let's get going. Oh, before I forget, this is a picture of a Wolf-Rayet star. This is the end stages of the evolution of a very massive star, more than 25-ish times the sun's mass. This is what happens before it goes supernova, and that'll be important. Okay, so first of all, what are short-lived radionuclides and how do we know about them? And the thing that lets us know that our solar system had radioactive elements, isotopes, with half-lives of less than a few million years is from meteorites, and in particular, inclusions in meteorites called calcium-rich, aluminum-rich inclusions, or CAIs. And if you look at asteroids, such as this, I think you see my cursor, great. Pieces of asteroids sometimes break off and fall to Earth, and here's one collected by my co-author Emily Benham in Antarctica. And when we take these back to the lab, we can see polish them and look at these little inclusions. And some of these white minerals are very rich in calcium and aluminum, and these can be analyzed. And these are the first things to form in the solar system, and they are dated to something like 4,568 million years ago. And we know that they contained radioactive elements, even though these radioactive elements have half-lives of only few million years. One of the most important of these is aluminum-26, which has a half-life of 0.7 million years. And of course, these all formed at the birth of the solar system, these CAIs, which was 4,568 million years ago. So none of the aluminum-26 exists today. But we nevertheless know that it was there through isotopic studies that produce graphs like this. So this is an isochron. What is done is to analyze different spots within the CAI, put your probe from a mass spectrometer, you're probing little micron-sized spots within the CAI. And at each spot, you're getting the ratio of aluminum-27 and 24 magnesium atoms, and you are also getting 26 to 24 magnesium ratios. In this case, it's plotted as an excess of that ratio above the standard value on Earth. And what you can do then is plot the data, and you'll see that it's a straight line. And what you expect if it was just a CAI that formed at high temperature at the birth of the solar system, you'd expect its minerals to have different aluminum and magnesium abundances, but you wouldn't expect the magnesium isotopes to be different in any spot. So you'd expect a straight line, but one with zero slope. But in fact, we see it has a positive slope, and that is because minerals that incorporated more aluminum-27 incorporated more aluminum, and some of that aluminum was aluminum-26. And subsequently, that aluminum-26 decayed to magnesium-26, and so minerals that have high aluminum have high magnesium-26-24 ratio. And the higher it is, the greater the slope, and you can actually plot the information like this, and you'll see that you're defining a line. So if you plot the data and you do a linear regression and you do it correctly, you can get a slope, and that will tell you how much aluminum-26 relative to aluminum-27 was in your sample at the time all of those crystals formed. And by doing this on many hundreds of CAIs, almost 1,000 CAIs now, it's seen that the vast majority of CAIs formed with a ratio that is 5.23 times 10⁻⁵. And we can infer that this is the amount of aluminum-26 that was there at the birth of the solar system. A lot of the chapter that we wrote for the Proof of Stars and Planets book, though, is talking about the caveats with this analysis and why you have to be careful. Another isotope that we look at is beryllium-10. It has a half-life of 1.39 million years and decays to boron-10. And if you plot the ratio of beryllium-9 to boron-11 and plot the boron-10 to 11 ratio against that, the same sort of thinking applies, the same math applies, and the slope should give you the initial abundance of beryllium-10 versus beryllium-9 in the solar system at the time it's formed. And here's an example of where that technique has worked well. Now, if your sample formed and then later it got heated so that the boron atoms in the sample could move around, could diffuse, then that will tend to average out the boron-10 to boron-11 ratio between all the points. And so they will tend to all have something closer to the average. That will reduce the slope. And then you'll also raise the intercept here. And if you then let it cool so that the boron isotopes no longer move around, then it will continue to decay. But what the final slope you get from this is going to be is one where you're looking at the beryllium-10 to 9 ratio at the last time it got hot enough for the atoms to diffuse around. It's also possible for water to interact with these systems, and water can react in ways that mobilize boron in some minerals and not others, and so you can get randomness like this. And sometimes this means you don't have a good fit for your line, but nevertheless you might suspect that you're seeing evidence of beryllium-10 anyway. However, you have to be careful. It's also possible to make boron by cosmic rays hitting the oxygen in these minerals and creating new boron, and it turns out that it will make more boron in minerals that, it makes the same amount of boron, but relatively more boron in minerals with low boron. So that will raise the slope, and it won't even affect the fit. And so you have to be careful to correct for those things when you talk about, especially beryllium-boron system. And so that's the beryllium-boron system. We have a lot of examples like that. We can also look at the aluminum-magnesium system like I showed you before, and it's sometimes instructive to look at different minerals. In this case, you might get measurements in spinel and diopside and malachite, anorthite, all these different minerals, which I coded with different colors here. This is actual representative data. And then you might see that it's disturbed, and it doesn't actually fit a straight line very nicely. However, you might look at this and say, yeah, but these minerals have not been disturbed. Anorthite is one where the magnesium atoms can diffuse around very easily, not so much in these minerals. And so you might, based on that knowledge, have confidence that this is the slope represented by these minerals, and this mineral is simply disturbed and you ignore it. So there's all these caveats with isochrons, and we have to know when to take it seriously and when to not take it seriously, but it's a really powerful tool. So this general technique has been applied to at least a dozen isotopic systems, and so we now know of the existence of over a dozen short-lived radionuclides. They're ranked here by their half-life. The shortest one we have confidence in is calcium-41, which decays to potassium-41 with a half-life of 0.1 million years. And there are many that maybe are too long-lived to be called short-lived radionuclides. Somewhere around 10 or 20 million years might be where we cut that off. But nevertheless, we can see the evidence of all these isotopic systems, and the slopes of their isochrons tell us the relative abundance of those elements at the time.
And so, yeah, there's an incredibly vast literature in all of this. Okay, so why do we care about these? They are extremely important for many reasons, and the most important reason to me is that they are useful for chronometry. So as I said, if you start a CAI with a slope of 5 times 10 to the minus 5, and then you see that later it was heated, and so you averaged all of the isotopes, reduced the slope, and then you let it decay, it'll end up with a final slope that is smaller. And by seeing a smaller slope, you can tell how many half-lives existed between when that reservoir first formed and when that CAI closed. And so an example is another inclusion in meteorites is called chondrules. Chondrules, you can also measure the aluminum and magnesium isotopic ratios, and you see that typically they have an aluminum 26-27 ratio. It's well defined, but it's usually lower. And this is actually a histogram from 2009 of how many chondrules there are with different aluminum 26-27 ratios at the time that those systems close. And this tells us that they're lower by typically a factor of 8, lower than CAIs. And that means that they closed or formed at a time roughly 3 half-lives, or about 2 million years after CAIs did. That's assuming that they all formed from the same reservoir with the same amount of aluminum 26, but assuming that is true, then you can tell when different things formed. And it's not just the aluminum magnesium system, but it's potentially any of those. And manganese 53 is one that's used a lot. Hafnium 182 is another that's used a lot. And those 3 systems especially have been used to date when things happen. Another very important reason to care about short-lived radionuclides is that they decay and release energy, and in fact it's aluminum 26 that the decay of that is what melted asteroids. And at least in our solar system, we know that there are many asteroids that basically, if they formed in the first 2 million years, they had enough aluminum 26 to actually melt rock. Iron 60 is a different short-lived radionuclide that has been suggested to also heat these asteroids. It does not. It's not abundant enough to do that. So asteroids are melted by aluminum 26 in our solar system, and we'd really like to know, is this a universal process? Do other solar systems have as much aluminum 26? Do they have more? Do they have less? Because that will determine whether the building blocks of planets in those systems melted, and if they melted, they may be dehydrated, or not. If they never melted, maybe Earths in those solar systems created 10 times more water. So we'd like to know where these come from and how much there is. And short-lived radionuclides, by virtue of emitting energetic particles like aluminum 26, when it decays to magnesium 26, it ejects a positron. It can actually ionize hydrogen gas, and this is very important for any studies of magnetic effects. There are parts of the protoplanetary disk in which our planets form that are so shielded from other sources of radiation that this would be the dominant source of ionization. And mostly, though, they also tell us about the type of environment in which the sun formed, because these short-lived radionuclides have half-lives on the order of 1 million years, and star formation takes on the order of millions of years. So there is certainly, since they were first discovered, there's been this inference that short-lived radionuclides don't stick around very long in the galaxy, and therefore it's almost a coincidence that they exist in our solar system, that the source of these must be very close to our solar system, to where the sun formed. I love this fact that the isotope of aluminum 26 was discovered in 1955, and within months, Harold Urey had figured out that this would be the isotope that would melt asteroids. And he also mentioned in the paper that the half-life was comparable to the time it takes to form stars, which had just been determined from protostars in the Perseus cluster to be on the order of 1.5 million years. So he recognized that the source of aluminum-26 must somehow be associated with high-mass star-forming regions, or at least with star formation, and that it would lead to asteroid melting. And it took another 20 years for evidence that aluminum-26 existed in the solar system to be found in meteorites, but Earl Jury got it right 2 decades ahead of time. So, yeah, they definitely can tell us about where the sun formed and what sort of star formation environment we formed in. But we have to figure that out. And there are 3 main hypotheses, or at least classes of hypotheses. I've called them injection, irradiation, and inheritance. Injection is one of the oldest ideas, that you have the sun's molecular cloud core that will be about to collapse to form a star, or maybe the sun and its protoplanetary disk, and they're next to a massive star that will go supernova, and the supernova injects that material into the disk or cloud. And that would be a source of newly manufactured radioactive elements. Another idea is irradiation, where you have energetic particles. It could be galactic cosmic rays, but usually these models invoke energetic particles like MeV to GeV, protons accelerated by solar flares, and the early sun had a lot of solar flares. And these would go out and interact with material in the protoplanetary disk and create new isotopes that could be radioactive. And then finally, inheritance that says, no, they were in the molecular cloud already, and we just got them because that's what molecular clouds naturally have. And each of these has different implications for how the sun formed and how common or rare any of these things are. So to go through some of these examples, injection. It could be that material was injected into the sun's protoplanetary disk. Then, so there's all classes of models, including some we've explored with my student Nicolette. Or they could be injected into a molecular cloud like this. And in the case that they're injected into a molecular cloud, because star formation typically takes millions of years for that cloud core to collapse, very often people will say that the supernova shock that would inject the material would also trigger the cloud to collapse, and thereby make it more probable that the material will be in there. So there are entire classes of models that look at those sorts of things. And then there are the question of what is that source? Is it a supernova, like a core collapse supernova? Or is it a Wolf-Rayet wind, the stage that precedes a core collapse supernova? Any star more than 8 solar masses will collapse at its end of its life and then go supernova and eject material. But if you're more massive than 25 solar masses, then there's a stage before the supernova where you're blowing up many solar masses of material that contain radioactive elements as well. And those are really the only plausible sources. But, you could have either one of those, and they could be injected into the disk or the star formation. And if you subscribe to this type of model, then you would expect that there should be some meteoritic samples, especially if it's injected into the disk, some that predate this injection, and therefore lack calcium-41, aluminum-26, but they might contain beryllium-10 because beryllium-10 is not produced by nucleosynthesis in stars, it's produced by irradiation in molecular cloud. So that would be one prediction. And you would expect that aluminum-26-27 ratios would be very heterogeneous across samples. Then there's irradiation within the disk, and this happens because, again, you have energetic protons that are accelerated by solar flares. And if one of energy, 10 MeV, hits an aluminum-27 nucleus, you can knock off a neutron and create an aluminum-26 nucleus. You can also spall oxygen-16 and produce beryllium-10, and so on. And so many models have explored whether you can explain all of the short-lived radionuclides using these sorts of processes. Some things to note are that these energetic particles do not penetrate very far, maybe a column equivalent to 10 grams per square centimeter, maybe 100. But the protoplanetary disk probably had thousands of grams per square centimeter thickness where the Earth formed and where meteorites formed. And many studies have shown that most of the energy of these energetic protons does not actually go into nuclear reactions. Really, 1 part in 10 to the 7 does that. So most of it is lost to ionizing hydrogen gas. And so you really need a lot of solar flares. And so that's an issue with these models. But a way to test these models is to look for variations in the beryllium-10 to 9 ratio. Of all of the radioactive species, beryllium-10 is probably most easily produced by this irradiation process. So if you see the effects, you should see them in that isotope first, and it's predicted that you should have higher ratios the closer you are to the sun. That makes sense. And it also takes time to build up, and so later formed samples should have more beryllium-10 than earlier formed samples. And and so if aluminum-26, for example, is produced by irradiation, then beryllium-10 certainly would be, and it should exhibit these sort of spatial and temporal heterogeneities. Okay. And then finally we have inheritance. It's already in the molecular cloud. And the idea here is that you have aluminum-26, iron-60, whatever, is always being created by stars in the galaxy. Massive stars explode as either supernova or Wolf-Rayet stars, and inject this material into the interstellar medium generally, and this collapses into molecular clouds, and then we get the molecular cloud material as the sun forms. And then separately, beryllium-10 is not produced by stellar nucleosynthesis, but it is easily produced by galactic cosmic rays hitting carbon, nitrogen, or oxygen nuclei in the molecular cloud. So beryllium-10 could just be created and uniformly distributed in the molecular cloud, and even the other radionuclides might be as well. And if this is the source of radionuclides, then you would expect them to be pretty homogeneous in the molecular cloud and mixed more thoroughly as the cloud collapses, so that pretty much all materials in the early solar system should form with uniform beryllium-10-9 ratios and 26-27 ratios. All right, so let's see how each of these models fares when tested against meteoritic data. And I'll start with the irradiation model. My colleague Emily Dunham has, for her thesis, compiled a tremendous amount of data on beryllium-10. She doubled the amount of analyses that existed in the field through her measurements. And so you can make a sort of histogram or plot of the beryllium-10-9 ratios in all 60 or so CAIs that have now been analyzed. And you see that they're all pretty uniform, and in fact, you could also plot it as a histogram like this. There are some types of CAIs that are a little anomalous, and yet if you only look at the 50 or so that we have great confidence are recording the initial value in the solar system, and they have not been disturbed, and they haven't experienced all of those cosmic ray spallation after they formed. If you account for the caveats and you look at the 50 or so that are, we have great confidence in, they're all very consistent in a very statistical sense with a single value, and that single value is 7 times 10 minus 4. So yeah, again, some existed on the surfaces of their asteroids, and if you're not careful, you might be fooled by these things, but they're all very uniform. And in contrast, the irradiation models would predict that 50% or more would deviate from a single value by more than 2 sigma had they formed by irradiation in the disk. And we're seeing no evidence of that whatsoever. So this gives us great confidence that irradiation contributes very little to beryllium-10 in normal CAIs, and if it's not producing beryllium-10, it's producing an even smaller proportion of aluminum-26, maybe use 53, etc. So I think we can effectively rule out irradiation within the solar nebula as a source of these radionuclides. For inheritance, we need to find samples that we think can tell us simultaneously the amounts of aluminum-26, manganese-53, hafnium-182, and have them tell us when those samples formed. One of the best examples to do this with are achondrites. These are meteorites that come from asteroids that have melted. So what we're looking at are rapidly cooled lavas on the surfaces of these asteroids that eventually get thrown to Earth as meteorites. For example, this angrite orbiting. And being a rapidly cooled lava, all of their isotopic systems should give us the same answer for when that formed. The aluminum magnesium systematic should say it formed at 5 million years, and therefore also the manganese-53, chromium-53, they should tell us the same age. All of these systems should say, yeah, they formed at 5 million years if it was a rapidly cooled lava, and if all of these radionuclides were uniformly distributed in the disk. So that any sample, this asteroid, that asteroid, all of these asteroids are sampling the same reservoir. So if that assumption is true, all of these should tell us the same time of formation. And for that matter, lead-lead dating should also tell us the same time of formation. The lead-lead system is a little bit different from what I've described already. It tells you exactly how old that sample is, but if you know how old time zero is, like the time when CAIs were forming, then you can figure out when after CAIs that achondrite formed as well. So we have 4 isotopic systems that we can compare, and we can see whether they're giving us the same answers or different answers, whether their chronometers are concordant or not concordant. To do this, we have to recognize that we have a formula like this for the time of formation based on the mean life of aluminum-26, it's the half-life over the LM2. And the formula is simple. You take the initial value in the solar system. This is like 5 times 10⁻⁵, and we know that because we've measured so many CAIs that we know that's just the value that existed in the solar system when they formed. You can look at the slope of your isochron and say that is the value when that CAI or that chondrule or that achondrite formed. And just taking the simple formula, the natural log of that ratio, multiplied by mean life, you have how long after CAIs that achondrite formed, according to the magnesium system. And you can do the same for manganese-53, but here we have a problem that we don't really know the initial value in the solar system of the manganese-53-55 ratio. We have a good guess, but not good enough for this purpose. So we have to consider that a free parameter. We also don't really know the half-life or the mean life of manganese-53 to better than like 20%. So we should leave that as a free parameter. Same for hafnium-182. You can measure the isochron, get an initial value in an achondrite, compare that to the initial solar system value, but we don't really know that either. So let's let that be a free parameter. And for that matter, if you were to get a sample that formed at time zero and has never been disturbed, we would like to know the lead-lead age date of that. And so people think we have samples like that, but I think we don't. So let's at least just leave that as a free parameter as well. So there's really 4 parameters here. The manganese-53 values, this one and this one. 4 free parameters to work with, but we have lots and lots and lots of data. And those 4 parameters should be the same for every asteroid we look at. So let's see if we can make it work or not. So that was the point of a pair of papers that I led in 2023 as well. We looked at 14 different achondrites listed here in this table. We looked at all the measured values in the literature for the aluminum-26-27 ratios in those. Some of them have them, some don't. Many have manganese-53 isochrons that we can get the slope for. Many have hafnium-182, 180 isochrons. We can get that slope there. So we get these sorts of values. And then we can define a time of formation according to each system for each of these achondrites. And then we can also get the lead age. So we chose 14 achondrites when we knew the lead ages. So we have really 38 pieces of data that should play nicely together across these 14 achondrites. And now we only have 4 parameters. We have 38 pieces of data. So it's definitely an over-constrained problem. And we can ask, are there values like for these numbers here that let this aluminum 26, 27 age equal this means 53, 55 age equal this happening age, an age you derive from these isochrons that would also match lead. That's the question. And we found that there is an optimal fit of those 4 parameters that allows everything to match. These are the values we infer from our statistical analysis. And we would say the half-life, or the mean, this should say the half-life corresponds to 3.8 million years, plus or minus 0.23. That is definitely consistent with measurements, 3.7, but the uncertainty on those measurements in the 2 sigma sense has been 0.7 million years. And in the 2 sigma sense, we can say there's only a smaller range that's consistent with the data being all concordant. Likewise, people have estimated the manganese 53-55 ratio at the birth of the solar system. We find a value that's in line with that. 182, 180 hafnium. This has been the estimates based on direct measurements from like CAIs and other inclusions. This is what we get from the achondrites. So that's another important thing. This is a direct measurement of the half-life. This is a model parameter. This is a compilation of many, many different types of inclusions and direct measurements of those. These are our inferences, but they're such a great match. And direct measurements of CAI lead ages, that's been done 4 times. And they come up with a value 4567.3, but our model says that's not going to be consistent. To find consistency across the chronometers, it has to be 4568.35. And these are not the same, but I just don't think that the lead measurements of CAIs are actually measuring the time those CAIs formed. I think it's measuring a later transient heating event that let the lead isotopes move around and diffuse through the CAI. And so there's a lot of reasons why these measurements shouldn't be trusted and this should be. And I see Maxime Perel is online and also made the same point in their paper. So if we take these optimal values, we can then say, all right, when did D'Orbigny form? According to the manganese chromium system, this is the initial value in the solar system. I have the isochron for it, so when did it form? And that number is in green. This is time of formation after CIs, and it's in green, this little Mars here. Red is from the aluminum 26, purple is from the lead dating with our values here, and blue is from hafnium tungsten. And you can see that you can take an average of those, that's the dotted line, and you can get an average time according to all the systems when that meteorite formed, and you see that all 4 systems statistically agree with that time of formation. They're all consistent, so those are all concordant. And you can do the same for this one, Sahara 99555. All of their ages are concordant. Out of 38 measurements, 1 or 2 are off by like 2 sigma. That's what you'd expect in a distribution like this. And in fact, in a very statistical sense, these are all concordant. There is one exception here, NWA 4801. We noticed the hafnium tungsten age is off by more than 2 sigma, but it also turns out tungsten is super abundant and anomalous in that one. That was a surprise. So, but we have 37 formation times and 14 achondrites with a chi-square of 1.09. Like these, there's no evidence whatsoever for any heterogeneity in the initial abundances of those. And in these papers, we also show that these other 2 systems, Hainan 129 and Beryllium 10, also appear to be uniformly distributed. So that was a test of the inheritance model, and it easily could have falsified the inheritance model. This is a very rigorous analysis. It did not falsify it, and so we have confidence that these were all uniformly distributed and inherited. Now, let's get to the injection model. There's been a long-standing viewpoint that there are there are some CAIs, and there are some CAIs that record very low values of lumen 26-27 ratios. HAL is an example. It's Hibonite and Allende meteorite. The slope here is like 5 × 10⁻⁸. If you had to wait for a lumen 26 in a normal CAI to decay to these levels, you'd have to wait 8 million years, and we know that it was already in the meteorite not doing anything in 3 million years. So this is really far too low to have an explanation of it forming from the same reservoir and waiting or something. And there's a few other objects like this that are inconsistent with forming from the same reservoir and being reset later. And they also tend to lack calcium-41, any evidence for calcium-41. So in a different paper that we wrote in 2023, my colleagues and I showed that, yes, these exist, but they are also weird. They are a distinct population, small, like hundreds of microns or smaller, grains of always hibonite or corundum. And this strongly suggests that there is a difference. It's chemical. It's not due to them forming before injection. It's not due to forming in a different place. It's a chemical heterogeneity. And so we showed that as the solar nebula collapses from the molecular cloud, and you start with a bunch of pre-solar grains, there's a difference in which grains carry lumen 26, and lumen 26, light lumen 26 is carried by small grains which are too electrically charged to accrete with other grains in a very close-in environment to the sun. So there's a way to make these low lumen 26, 27 inclusions. We call them low lumen 26, lumen 27 corundum hibonite inclusions or latches. And but they're weird, and there's a special time and place in the nebula. But it certainly does not demand that there was a time in the nebula where there was no lumen 26. And indeed, if that had been true, then you wouldn't see the concordance among the chronometers. So that's really strong evidence for inheritance. And that works for most of the radionuclides, but as I said, beryllium-10 is a little bit different because it is produced by spallation. So instead of supernovas injecting that radionuclide into molecular clouds, you have to have a molecular cloud where these cosmic rays come in, they hit oxygen nuclei, and they create beryllium-10 nuclei. And it's a very old idea. Like, as soon as beryllium-10 was discovered, it was suggested this may be the case. But the ratio that you expect from this naively is the amount of beryllium-10, the beryllium-10 to 9 ratio that you expect to get is always much less than 2 × 10⁻⁴. But the values we see are like 7 × 10⁻⁴. And so this discrepancy kind of prevented some acceptance of this model that the beryllium-10 is just all made in the molecular cloud. But I think since then we've come to realize that, first of all, cosmic rays, the rate at which cosmic rays go through a molecular cloud is proportional to the rate of supernovas, because it's when supernovas explode a shock gas that actually makes cosmic rays. So because the star formation rate, and therefore the supernova rate, was actually higher by a factor of 1.5 to 2 when the sun formed, that helps a lot to make more beryllium-10, but it's still too low by factors of a few. However, in this work, we realized that actually, if the sun is forming in the spiral arm of the galaxy, the molecular clouds are seeing a much higher rate of nearby supernovas. Many more massive stars exploding, making cosmic rays in spiral arms in galaxies, and that is actually where most stars will form. So if you just look at a volume average in the galaxy, this like here by average location, the blue line, and you ask what's the typical galactic cosmic ray flux you get, you infer that most of them have a sort of low value. Let's say this is proportional to cosmic ray flux. But if you take into account that The places like where you have the highest cosmic ray fluxes are the spiral arms, which is where most of the stars are, and you weight it that way, you find that actually most stars see a high cosmic ray flux, and that kind of resolves the discrepancy very nicely. So 7 times 10 to minus 4 turns out to be a very typical value you would predict for how much beryllium-10 is produced by cosmic rays in the molecular clouds of the sun formed. And so this begins to let us see the sort of star-forming environments where the sun would have acquired its radionuclides. We have great confidence then that the beryllium-10 is in the molecular cloud, and it was in a spiral arm of the galaxy, and the other radionuclides must have gotten into the spiral arm molecular clouds as well. And that is consistent with what we actually see from astronomical observations of aluminum-26 and iron-60. Those two radionuclides, when they are injected by supernovas or by Wolf-Rayet stars, they go into the interstellar medium, and they begin to decay, and part of their decay is to emit gamma rays. And these gamma rays have been observed, and this is a map of where aluminum-26 gamma rays are coming from in the galaxy, and you see not only is it concentrated in the galactic plane, but in certain spots, basically where you have regions of high mass star formation. And so it's easy to imagine that the sun formed in a spiral arm where there was a lot of high mass star formation. That's where the aluminum-26 is. These are now simulations by my collaborator Yusuke Fujimoto, simulations of galaxy evolution, where you see where stars are in a spiral galaxy like our Milky Way, where gas is, but then also keeping track of where the stars that explode are and where the aluminum-26 they produce is. And the point is that it's very patchy, and you get an average amount in the galaxy, and that's actually, that average amount across the galaxy is kind of low, and would lead you to predict aluminum-26 ratios that are too low. But once you account for the fact that it's very patchy, and regions like where the sun would form might have a very higher concentration, then it all starts to make sense. And this is an animation, yeah, it does work, of how the galaxy would evolve and where aluminum-26 and iron-60 would end up being, and it's kind of fun. But these isotopes are injected into spiral arms. They get into molecular clouds, and normally gas kind of goes through a spiral arm and comes across the other side. But because the timescale by which these radionuclides goes in and out is so rapid, it never actually leaves the spiral arm. It builds up in spiral arms. You can make predictions on how much aluminum-26 and iron-60 different solar systems should be born with. And this is the distribution. You got, there's a slight improbability with the amount of iron-60 you get, but the amount of aluminum-26, this is the sun. The amount of aluminum-26 the sun has is very much in line with this distribution. This kind of implies that it's not just supernovas that are making these radionuclides. It might be dominated by Wolf-Rayet winds. I'll get to that in a second. But the sun is mostly normal in the amount of aluminum-26 it has for stars born in spiral arms. So one thing that has been done to drill down further into this is to look at all of the radionuclides and their abundances and plot their abundances against the half-lives of those, or the mean lives of those radionuclides. I'm not going to actually describe this model. I'm going to describe the one that works, and that is regional self-enrichment. As I've just described, you have supernovas going off, and they contaminate molecular clouds, and then it gets into newly formed stars. My co-author Ed Young worked on this. There's basically 3 parameters in the formula that says the abundance, this ratio, this abundance of any radioactive element should be related to its mean life, and just 3 parameters. And that is this best fit here. Those parameters have to do with what fraction of the gas is in molecular clouds at any moment, how long it takes for gas to cool to form molecular clouds, and the ratio of how much material getting into clouds comes from Wolf-Rayet stars versus from supernovas. So an unexpected surprise is that a lot of the material has to come from Wolf-Rayet stars. At least the material that gets into molecular clouds has to get from Wolf-Rayet stars, not supernovas, but otherwise the model predictions with 3 parameters match these dozen or so radionuclides very nicely. So the convergence between the numerical simulations and this sort of analysis for meteorites tells us this is probably how we acquired radionuclides. There's one, you can see that this Chlorine 36 doesn't quite match as well, and there is an uncertainty envelope that gets worse as you get to short half-lives, but Chlorine 36 is a little bothersome. But it turns out Chlorine 36 has a very short half-life, but nevertheless we know it doesn't quite work. But the evidence for it is only found in CAIs that have been aqueously altered at late times, and long story short, we think that this is the one radionuclide that does show evidence for production by irradiation in the disk. And so you probably have a stage late in the evolution of the disk, maybe at 3 million years, where flares can send energetic protons directly into the gas, produce Chlorine 36. This can get into ices that get into asteroids, and when the ices melt, the Chlorine 36 they bear can react with minerals. All right, so to wrap up, this was an analysis of a review of what had been done since the previous Protostars and Planet 6 meeting, and there were many, many new analyses, especially for beryllium-10, but also across all the isotopic systems, a lot of lead-lead systems. So it was an update of all of those ages, but we feel like the story is finally setting for where these radionuclides come from. And inheritance from the molecular cloud, I think, is strongly favored for almost all of the radionuclides. Beryllium-10 is produced by irradiation, and the others are produced by this mixing between newly formed supernovae and molecular clouds. There's really not any evidence, nothing compelling for late injection of supernovas directly, like a single supernova into the molecular cloud or into our protoplanetary disk is pretty much right out. And irradiation within the disk can be eliminated too, except for Chlorine 36. So that means you can use these radionuclides, given that they were uniformly distributed in the disk. You can use them for chronometry, and then we can ask if these rare inclusions that lack Chlorine 26, is this really telling us that they formed before, or is this just some weird thing about them? And that's what I think is going on. And then we can infer what other solar systems should be like, and given that the sun appears to have formed in a high mass star forming region and is similar to where most stars form, we can infer that the sun was pretty typical. You should have similar, and what I mean by this is maybe 90% of solar systems should have aluminum-26 abundances that are within 1 order of magnitude of what the sun had. So there could be some systems where there was never enough aluminum-26 to melt asteroids, and there could be some where they melt even a few million years after ours, but ours is not an atypical thing. And supernovas and Wolf-Rayet winds both contribute to aluminum-26 and iron-60 gamma rays that we observe, but only the Wolf-Rayet winds appear to have gotten into molecular clouds with implications for star formation. And with that, I think that is all I have to say. And the conference was in Kyoto, so I wrote this poem saying, meteorites fall from the sky like petals. They tell the story of the star flower. So, thank you for your attention.
Thank you very much. We're going to do hybrid questioning. So we've got questions from the audience. We're going to ask people online to raise their hand and ask their own questions. Previously, we put the questions in the chat. I think it was a bit stilted. So if you're online and you want to ask a question, you raise your hand, we'll get you to ask your own question, and Steve will talk to you directly. So if there are any questions from the audience, Ben?
So there was a paper recently by Cecile Deligny about aluminium magnesium disturbances in Deligny. Deligny's used a lot of anchoring for lead ages and stuff like that. Do you think Deligny should still be used as an anchor for a lot of ages? And if not, what do you think should be used as an anchor?
Yeah, D'Orbigny is commonly used one, and because it's commonly used, there are many analyses that you can use to beat down the uncertainties. And I think you're safe if you use bulk measurements. I think even if you see some heterogeneities on small scales, the bulk is what you expect to be consistent, chronometrically, and it appears that it is. So I would continue to use it. And however, the more, the better. The success of this statistical technique is that instead of anchoring, you get a difference in age between this meteorite and that meteorite in this system, and you compare it to the difference in age from this system to that system and that other meteorite. This says just use statistics, average it smartly to get these initial solar system values, and then you get increasingly precise ages of things. And so, yeah, the more the better. The more you average, the better. And averaging also probably alleviates some of those concerns about heterogeneity.
We've got a question from Ankit. I don't know if you can you unmute yourself, Ankit, and just try asking a question?
Yes.
Okay.
Hi, Professor Desch. So I have a question regarding the calcium-41. So if we look at the energy cross-sections of calcium-41, we can see this easily produced by solar energetic particles. But the meteoritic evidences say otherwise. We have a low ratio of somewhere around 10 raised to minus 9. And then there is question of beryllium-7. That is also have been, it is also produced by SCPs. So can we really rule out the SCP production of SLRs apart from 36 chlorine?
Yes, we absolutely can. And I presented at LPSC this year about the beryllium-7. There is no evidence whatsoever for beryllium-7, and there have been 3 papers claiming it, and they're just wrong. And they have not analyzed their isochrons carefully. They haven't taken care of some of these caveats as I've described. Beryllium-7 only has a half-life of 53 days. It would be incredible if an inclusion could form within a few months that would record that, and indeed I don't think we have any evidence for it. Flares happen near the sun, and the gas very near the sun is sure to be irradiated. You can produce any of these radionuclides there, calcium-41 included, but that is a very different question from asking, did those radionuclides end up in CAIs, into the meteoritic inclusions that ended up in meteorites in the asteroid belt at 2 to 3 AU? And I think they simply just did not.
For your thanks for the talk. First off, I really enjoyed it. For your test of inheritance model you've got there,
Yeah.
you've measured a bunch of anhydrides, which are inner solar system materials. I'm not familiar with the other ones, but are they all inner solar system, or is there anything outer that you've measured there?
Right. Yeah. So I compile data. I'm not to be trusted in the lab, and but we compiled quite a lot of literature data. I think there's over 50 papers here. And almost all of these are NC, but NWA 6704 and I think 2976 are CC.
Okay, good. So it's not just a homogeneous inner solar system. You've
Right. Now, we had to get the best match here. It's an acceptable match if you don't do this correction, but it's an incredibly good match if you do make this correction. When you measure lead ages, you have to know the uranium-235-238 ratio at the same time. You have to correct for that. And the right way to do this is to get that uranium ratio in the same mineral where you're measuring the lead isotopes, pyroxene or something. But usually what is done is to get the lead-lead isotope ratios in the mineral through an isochron, and then to measure the uranium ratio in the bulk. And because of that, there's going to be a discrepancy, potentially. It depends on how much of your uranium is in the pyroxene versus the other phases. And we argued that whereas that ratio should be similar in NC achondrites, and it should be similar among CC achondrites, those might be different from each other because of the oxidation state of and that determines how much uranium fractionates it. And so we made a correction that amounts to 0.19 million years. On the scale, it's kind of small, but we're doing things at such precision that was important enough to do. So the CCs may have that sort of difference, and that's something that is being looked at, and I think it's driving me. I know Yuri Allen did something to this effect to test this, but he doesn't like the idea, but it's also unclear. But even if we don't make the correction, it's still a remarkably good fit. Thanks.
Any more questions? I was going to ask one question. In a situation in which you've got a very low amount of aluminium-26, and you don't really do much asteroid melting early on, does that have implications for terrestrial planet formation?
Like in another solar system?
Yeah.
Oh, yeah. It probably doesn't matter to an accreting planet whether the asteroids it's accreting have melted before or not, but it has been hypothesized, actually, Lori Leshin and I wrote an abstract back in 2004, but never followed up. But Tim Lichtenberg has worked a lot on this in recent years, where if you have aluminum-26, it may heat and melt the asteroid and dehydrate it. So it may cause water to escape the asteroid. And then that would mean that the planets you accrete from those asteroids would be depleted in water. And in a system where they never melted, they might have a lot more water.
So you could have lots more water wells in that.
Yeah.
A bit more questions? Yeah. Martin Miller.
Okay, naive question, possibly. We're starting with aluminum-26. It's in atomic form. It's generating, 3 MeV per decay. How does it get into a mineral when it's generating so much heat? I mean, we're talking about minerals, aren't we? Yeah, the starting material is atomic.
Yeah, so what happens is in a supernova or HB star or Wolf-Rayet wind, anytime it's leaving the star, the material that contains all these atoms, it cools. The atoms find each other and form minerals. It doesn't really matter that aluminum atom might decay a million years later. It goes into the minerals all the same. Corundum, hibonite, whatever minerals you form. So then this mineral might have so many moles of aluminum, and 50 out of a million of those atoms are aluminum-26. They do decay. When they decay, they emit positrons and neutrinos, and there's also a recombination. So you get several MeV of energy, but positrons escape a micron-sized grain entirely, as do neutrinos. You actually don't generate a lot of heat in the grain itself, so the mineral doesn't really care. But it matters if you make a planet, or a 100-kilometer sized asteroid, then the positrons and stuff that you gamma rays, they can't escape that, and so the heat is deposited inside an asteroid-sized thing. But a grain doesn't really care.
Okay. We've got a couple of questions we'll put into the chat. So Alan Rubin has asked, if chondrules were heated several times, then the aluminium-26 dates the time the last melting event. This would mean that the initial formation of the chondrules is pushed back in time, closer to the time of CAI formation.
Yes, and I think he's referring to this histogram. When you look at a bunch of chondrules and you see what aluminum-26-27 ratios their isochrones record, that tells you the amount of aluminum-26 in them at the last time they were heated enough for magnesium atoms to move around. And it could be that they were melted 2 or 3 times, and we're only looking at the last time. So certainly they could have melted earlier, and we just don't know.
And Harry Becker has asked, how far does your conclusion on inheritance of radionuclides from the sun precursor have consequences for the observed NCCC dichotomy on nuclear synthetic isotopes?
Yes. So as it turns out, we were talking earlier about how do we know which asteroids or which achondrites come from asteroids that formed in the inner solar system versus the outer solar system. And all asteroids show these different abundances of certain isotopes, like titanium-50 or chromium-54. Some asteroids have a higher proportion of their chromium as chromium-54, some have less. And they divide into 2 camps. We think they form inside Jupiter and outside Jupiter. But whatever it is, they form into these 2 camps. The differences are very small, on the order of parts in 10,000 in the ratios of those. But nevertheless, they exist. Those isotopes tend to, we think, go along with like they're very neutron-rich isotopes that are probably formed in supernovae, so they have something to do with supernovae. And aluminum-26 has something to do with supernovae. So you might expect a correlation between those. It's not clear what it would be. Personally, I don't think that the NCCC dichotomy, the stable isotope difference, has anything to do with inheritance from the molecular cloud. I think everything was uniformly mixed in the solar system, and then those isotopes were fractionated through chemical, thermal, and aerodynamic processes in the disk. They don't have to, have anything to do with each other. I can't rule out that they do. I hope that answers the question.
Okay, we don't seem to have any more questions online. Have you got any more questions from our audience? Well, in that case, I'd like to say a big thank you to Steve for a very, very fascinating talk. Thank you very much, Steve.
Thank you.
Just to let everyone know that we've got more EdScott talks lined up after the conference season is over, so in the fall or the autumn, depending on where you're resident. So thank you very much. Thank you.
So presumably the next step is to do the same inheritance test, but only with outer solar system materials.
The more the better.
Let's see if
It wants data.
I will say this, I construct easily falsifiable hypotheses.
That's the best type.
Have at it.